In the last couple of videos, we took a look at making use of this chain rule. And one thing that you might have noticed when you looked back at this chain rule is that this was actually labeled as just case 1 of the chain rule. In this specific case, we saw that our function z was a function of two variables, but the functions for x and y were functions of a single variable. This is why, like when we looked at example 1, we saw that if we plugged in the value for x and y, if we plugged in those formulas, we could essentially rewrite z as a formula with only a single variable. And this is what actually allowed us to go ahead and compute something like dz dt, not a partial derivative here, but notice like a full derivative. However, that might not always be possible. If it was the case that my functions of x and y were also functions of multiple variables, then the formula that I would have gotten down here in blue would have also had multiple input variables. Maybe say like t's and s's would have been floating around in there. And that would have made it impossible to get a full derivative of z with respect to one of those variables. I would have had to take a partial derivative. This is where case 2 of the chain rule comes in. You'll notice here that in case 2, again, I have z as a function of two variables, but I also have x and y as functions of two variables. And so in this case, I'm only ever going to be able to get a partial derivative of z, either with respect to the s variable, or a partial derivative of z with respect to the t variable. The rest of the setup for what's going on here, otherwise, is exactly the same. So let's take a look at how this works here with something like example number 3. Suppose that I have z equals this two-variable function, and y and x are also two-variable functions. How do I start to compute my partial derivative of z with respect to s? All right, so my partial derivative of z with respect to s, according to the chain rule, should be take the partial derivative of z with respect to one of its variables. So like, let's start with x. Then go to the x formula, and this time I'll also have to take a partial derivative because I have multiple variables in this formula. So I'll do a partial derivative with respect to s. Then I'll add on and I'll do a partial derivative of z with respect to the other variable of y. And then I'll go to that y formula and do a partial derivative with respect to s. All right, so let's see how that would work here with the given functions that I have. If I started off with a partial derivative of z with respect to x, I would have y as a constant, so that could just kind of sit outside of the derivative. And then I'd have to take the derivative of 2 to the x. Now this is kind of an obscure derivative rule from Calc 1, but its derivative would be 2 to the x times natural log of 2. It's always going to be the same number to the x, but just multiplied by natural log of that number that's in the base. And this works for really any value of number to the x, like even for e to the x. You might remember that the derivative of e to the x is just e to the x, but it also works in this format where you'd have e to the x times natural log of e. It just so happens that natural log of e is 1, and this would simplify out. Okay, so this is my partial derivative with respect to x for the z formula, but I would then have to multiply on my partial derivative of the x formula with respect to s. So in this case, that would be e to the st multiplied by the derivative of st, which should just get me t, since t right now is being treated like a number and s like a variable. I would then add and swap some things around. Now I'm going to do the partial derivative of z with respect to y. That's just going to get me 2x. And then I would do the partial derivative of my y, which should get me 2s plus t. All right, so I have my formula, again with a whole bunch of mixtures of variables. And it's totally fine now to start thinking about how I would actually go about evaluating this. So what I'm going to go ahead here and do is state that when s is equal to 2 and t is equal to 0, I'm going to figure out what the values of y and x are here, just so it makes the evaluation process a little bit faster. Notice here that if s is a 2 and t is a 0, for y I'm going to get back a value of 4. For x, I'm going to get e to the 0th power, which is the same thing as 1. So now I can say that when s is equal to 2 and t is equal to 0, we have that my partial derivative of z with respect to s should be equal to, and I'm just going to plug in all the values that I had for these different variables. So I'm going to get 4 times 2 to the first times the natural log of 2 times e to the 0th power times t, which is 0. Then over here, I'm going to get 2 to the first power. I'm going to get 2 times s, which is going to be 4, and finally plus 0. So this actually turns out really nice. This whole first term that's really messy is multiplied by a 0. So I'm really just going to get here 0 plus 8. And so my derivative just ends up as 8. So notice that there was not really anything different with the calculation process here, except that I just really had to be careful with my notation. I can't say that I have a full derivative of z with respect to s because, well, I can't get that because the functions that are further down, these x functions and y functions, don't have just a single input variable. The last thing that we want to make note of here is that it's important to recognize right now that these partial derivative symbols like dz or dy or dx, those partial z, y, and x, they don't really have any meaning in and of themselves, which was very different than like dx's, dy's, and dz's, things that we're very familiar with showing up in, say, like when we did integrals, specifically like u substitutions. We thought of those items as kind of individual components that could be moved around. However, the partial of z, partial x, partial y, those are not individual symbols. We kind of have to treat the entirety of these fractions, if you will, as a single symbol that can't really be separated. So because of that, one thing that we have to make sure that we're not ever going to claim is that, like, in here, my partial of x's are going to cancel. I can't say that. I can't say that the partial of y's are going to cancel. And it would actually be pretty easy to see kind of why that's the case here. Because notice that would imply that my partial of z with respect to x would end up being equal to a partial of z plus another partial of z. That is, one of those partials is equal to 2 of those partials. And that could not be true in general. It would only be true in the case where that partial is equal to 0. So I have to make sure that I treat these partial x, partial y, partial z notations as kind of not really individual items by themselves. They have to be considered with both the top and the bottom of that fraction in play in order to have any sort of meaning.